So in this video, I want to give a couple more examples of creating or defining a brand new function using a definite integral with a variable limit of integration based on a function that's already been given to us. I call these new functions area accumulator functions. Here's our first example. Given that g of t is equal to the definite integral from 1 to t of f of x dx, where the graph of f is shown here consisting of line segments, we want to calculate g of 3, g of 4, and g of 0. I'm going to go ahead and come over to a new page with that graph of f so that I can do some work on it, and begin by first writing what I was asked to do. First thing I was asked to do was to calculate g of 3. Using the formula that was given to me, I would just simply plug in a 3 and get that g of 3 is equal to the definite integral from 1 to 3 of f of x dx. Now remember, of course, that the variable that is in this place right here is the actual variable of the new function, whereas the variable that is over here in this is just a placeholder. And if you're a little confused still about the variables, that's fine. Come and talk to me about it, and we can try to get that cleared up. But the idea being that I have replaced the variable t with a 3. Now, what I have here is a definite integral that I need to calculate based on f. And what that is asking me to do then, we know that a definite integral basically represents area. So it's asking me to find the area from 1 to 3 underneath the function f. X equals to 3, or t equals 3 in this case, is actually an interesting place because f actually has a value of negative 3 at that x coordinate. However, that is only one tiny infinitesimally small point, and it doesn't actually affect the area at all. The area is going to be all the way from 1 to 3, including 3, up here above the x-axis. So I want to calculate that area in order to find the value for this definite integral. Well, that has a width, of course, of 2 and a height of 4, and therefore I get a value of 8. I could actually keep track of my various inputs and outputs as I create this new function g and go and graph it if I wanted to. We weren't asked to. But for example, what this is saying is that there is a point on this new function whose input is 3 and whose output is 8. Now I'm going to go calculate g of 4. For g of 4, I need the definite integral from 1 to 4 of f of x dx. Looking at my picture here, that means I'm going to start at 1, I'm going to end at 4, and I'm going to calculate the area between the curve and the x-axis. Up here, that area is positive, but then I jump down and get some negative area. So I have negative area here, positive area up here, both of which are going to combine to give me a net change or a net area. So in this case, again, I have the 2 times the height of 4, and then I have a width of 1 and a height of actually negative 3. So 8 minus 3 gives me a value of 5. G of 4, my new function g, has an input of 4 and an output of 5. All I'm doing is getting the area between the function f and the x-axis where there's both positive and negative areas, getting that net sum, and that is telling me the value for my new function g. I want to actually go and look at this on a calculator. The TI Nspire makes this really nice to look at. Here I have the function f graphed, and then I have a slider here where I can actually change the input. So as I change that input, you can see that it's giving us the value for the definite integral for that accumulated area. As I get here to x equals 3, or t equals 3 for my new function, you'll see that the value of the function, of course, is down here at negative 3. But the area is only consisting up here of this rectangle. And therefore, the definite integral is equal to 8. I continue moving along, and there we can see that we have a value of 5 when the input is 4. You'll notice as that I move along here, the definite integral is actually getting smaller and smaller in value, and that's because we're adding more and more negative area up until this point where x is equal to 5. And then we start adding more and more positive areas, so the definite integral increases. So it's just a nice visual to sort of see how we're actually calculating a value for the definite integral by accumulating that area. Going to bring this into our lesson over here so it can be saved. And as usual, like in class, I forget to add a new page first. So we'll bring that over here. And that just kind of gives us, like I said, a visual to go along with what we're doing here. So right here is my movable variable t that is getting plugged into the function g. And this area that is being calculated, that all added together is the value for g of t. So we have one last value that we were asked to calculate, and that is g of 0. And that would be the definite integral from 1 to 0 of f of x dx. We learned in class that we can flip the limits of integration if we take the opposite of the definite integral. So that is equal to the opposite of the definite integral from 0 to 1. Or in other words, the opposite of that area that I'm going to calculate. The area from 0 to 1 is right here. It has a width of 1 and a height of 4, and therefore I get that the definite integral is -4, g of 0 is -4. I could actually come back here and plug that into my chart. Again, we could do that for lots and lots and lots of inputs t, getting g of t, and eventually we could make a graph for g. But we were not asked to do that in this case. In the next example, however, we were asked to do that. We want to draw a graph of f of x equals the definite integral from -1 to x of g of t dt if g of x is x minus 1 e to the x. You'll notice that we've swapped out the letters again. So this right here is the real variable for the new function. This is the real variable for the new function, which is called f. This variable here is simply a placeholder that says how you are manipulating the formula. So that one doesn't really matter. This is the one that matters right here, and it's the one that's up here as our upper limit of integration. So in this case, we're actually going to use a graphing calculator to draw this for us because we want to do this at lots and lots and lots of x's. The calculator, of course, is very, very quick to be able to do this for us. And I will come up here and turn on a really big display so that you can see very clearly what it is that I'm typing in. So the first thing we do is we go in and type in our function that serves as the basis. Remember, this is not the new function. This is the one that we're basing everything upon. And we'll go and get a graph for that. And let's see, maybe a zoom decimal will work nicely for us, and it does. So then we come in here to y equals, and for y2, we're actually going to do an integral. And that is under Math 9. So this is using the new operating system. I'll go back in a second and talk to you about how it will look on the old operating system. But you would plug in your lower limit of integration. In this case, we were told that it was -1. Our upper limit of integration is that variable, so we're going to use an x. And then here I need to make it based off of y1. Remember that we use the vars key, move over to y vars, select function, y1. And then I will move over here and tell it that the variable that we're using in that function is x. Having set all that up then, I can now let the calculator point by point by point plot the graph of the new function, which in this case is called f. It's taking it a long time because for every single pixel, it's having to calculate a definite integral, and that actually involves a pretty intense calculation process, even for the calculator. It is not doing algebra to do this, it is doing everything numerically. And so it's a lot of number crunching it has to do. And because of that, it just takes it a long time. It takes it quite a while to actually draw that graph. But every single one of these points, the y-coordinate, is that area that is calculated from -1 to whatever point we're at, whatever x-coordinate we're at. That area, that definite integral, is giving us the y-coordinate, which is what we're then plotting to create our new function. And so now we're done there. We'll get a screen clipping of that to bring over into our notes as well. Yes, yet again, I forgot to add a new page first. So the one thing I want to do really quick before I forget is to tell you what it would look like on the old operating system or TI-83. For Y2, when you do math 9, it's going to put in the command fnint and open a parenthesis. At that point, you're going to go in just like we did before and do the vars thing to get your Y vars, to get Y1. Then you'll put a comma, which is just above the 7. You'll put the variable x, a comma, the starting limit of integration, which is -1, and then the ending limit of integration, which we are leaving as a variable. So that's what it would actually look like for you on a TI-83 or the older operating system of TI-84. And so there is the answer to the question. You would then just copy that graph into onto your homework if this is what your homework question we're asking you. One last thing I'd like to point out here is that there are some connections between the original function and the new function. You will notice that the original function has a 0 right here at x equals 1, and that the new function has a relative minimum at x equals 1. And that is not a coincidence. We will talk in class a little more about the connection between these two functions, but you might want to try to think about it for yourself and look in the book. So now that you've watched this video, make sure that you go down below the video and look at the description. In the description, there is a link for a Google form, and that Google form lets you answer a few questions and submit that to me so that I can see that you have actually looked at the video. If for some reason that link is not active, all you need to do is to reload this page and then go down there and click on that link to get to the Google form. Thank you.